Hi, good morning, and welcome to the ZP webinar on Sense It All. So we do like to do this webinar once a month, and it's really just updating on the Sense It All platform. So I will today I will have some slides, but I also want to say that there will be a genuine, let's say, live streaming demonstration as well. So in front of me, I do have the Sense It All. Since if you've come to one of these webinars in the past, this has changed considerably, really, over the last few months. That now, actually, it's becoming essentially it's become a potentiostat that could be used in an R&D setting, and it's also an instrument that could be used as a sort of minimally viable product, or also as a product in a kind of commercial translation of science out of the lab into um, out of the lab and into commercial settings. With that said, let me go forward quite quickly. So today I'll talk about point of care, point of need diagnostics. I'm going to talk about a technology stack that I think really accelerates the development of sensing in specific applications. So today I'll show you that this platform has, for example, nitrate, potassium on it. We also have a phosphate sensor at ZP that we haven't moved it onto the platform yet. So you're going to see that this platform is able to leverage many of the ZP, let's say, sensors. And you'll also see that it can actually leverage sensors that today don't exist, but actually the technology would allow you to then move those sensors onto the platform. Anyway, that's a lot of words. Let me kind of go forward, say that there'll also be a demonstration today of this platform as well. So as I say, it's not all words. I don't really like to do webinars that, let's say extra content in them. So we will be talking about doing a demonstration on this very shortly as well. With that said, let me go forward and just sort of say that. So today I'm going to talk about the Sense It All platform. I realize I don't actually have a wearable in front of me at the moment, but today I'm not going to talk about wearables today. I realize that when we try to talk about point of need testing and wearables in the same webinar, it's basically trying to put two webinars together, and it can end up with easily 90 minutes. So if you're particularly interested in wearables, then there's a wearables webinar next week, 28th of August. We always do one in the morning and one in the afternoon because it helps to cover various time zones. But as I say today, I am going to talk more about point of need testing. I will highlight that the instrument that I have in front of me today already has an assay for things that people are very interested in these days. Even though I sort of talk about point of care diagnostics quite a lot, there's also point of need testing. I mean, we tend to use this technology actually in food testing, but we've also launched a nitrate sensor on it and also a potassium sensor on it. Now, the nitrate sensor was originally developed and conceived for actually agricultural setting, though I think the initial customers were actually using it in the water sort of quality setting. Now, the potassium sensor was actually originally intended for potassium in human applications, because if you know something about medical diagnostics, there's something called the comprehensive metabolic panel, and there potassium is one of the markers. But what you find really interesting actually is that all these different applications often require the same sensor, but there may be a different matrix and a different calibration involved. So that said, today I'm not going to talk about wearables. Or at ZP, we do actually have a lot of technology in wearables, but it just leads to too long a webinar, and I would like this to be a bit more sharp and snappy, let's say. We do have something that's really quite powerful, right? What I mean quite powerful, I mean, this is the hardware. You'll see it in action. At ZP, if you want to make any kind of measurement technology, the the system has to be reproducible. You either have to have excellent calibration in place so that you can calibrate just before the point of test, or the system has to be repeatable. When you're talking about distributed testing, blood glucose is an example of distributed testing. There, it's calibration free, and you really can't expect those end users to do calibration. The reason I bring that up is because ZP, the heart of what we're going to talk about this afternoon, at the heart of it, there'll be something like a screen printed electrodes. And these are manufactured in many places by many people. It's probably worth saying that if these are not reproducible, then this entire premise that I'm talking about today will not work, because You've then got a new source of variability, which is actually the individual electrodes. So that's something that we've worked out really hard over the years at ZP. You will see an app in action this afternoon, and I know at least one of you has been to one of our webinars in the past. I'm going to show you that this app has come on a long way since you've last seen it. I'm also going to show, because in what I mean is come on a long way. Sense It All was originally, I would describe as an MVP, a minimally viable prototype. You could take ideas and develop them very quickly on it. Also understand now that your academic colleagues can use this as a lab instrument, as a potentiostat. So if they're developing glucose sensors, it's got amperometry. If they're developing ion sensors, things like phosphate pH, it's got open circuit potentiometry. If they're interested in making protein sensors, then things like impedance spectroscopy, it has it. If they're interested in small molecules, for example, could be omega-3, then linear sweep voltammetry, cyclic voltammetry, and square wave voltammetry are all on the platform now. But that will become more clear as I go through this. This is really significant, and I haven't actually sort of discussed it so much in the past, but this technology is immediately cloud enabled. That is important because what it means is we can actually send the data automatically to the cloud, which is really important in any kind of monitoring. If the data is then kind of resident on a local drive somewhere, it's very hard to scale with that information. But we actually send it all to the cloud. So with a cloud system, you can monitor users and you can really kind of scale the impact of that data. Hopefully, when I actually do the demonstration, that'll become a little bit clearer that. So we have electronics, and as I say, this has actually become more than just an instrument that I would say for months. In fact, now it's actually become a lab instrument as well for doing things like standard electrochemical assay development. So I'll talk about the hardware today. We'll also talk about screen printed electrodes. We'll definitely talk about the app, and there'll be some QR codes popping up. When those QR codes popping up, you don't need to do anything in real time because it'll be too hard to sort of scan the QR codes. But if you watch this recording later on and show it to colleagues, they'll be able to actually install this app on their phones. And so they'll really get a sense of actually this is already to some degree distributed, at least the software is distributed. And then it'll actually allow you to play with the cloud as well. And the cloud has a data pipeline, which I will discuss today as well. It also has an API built into it, an application program interface. So for example, if you were doing water quality for some process and the data ended up in our cloud, you might because you want to sort of marry it with other kinds of data. Just make sure I didn't knock my microphone off then. With that said, let me go forward with a few more slides. So this is the way the system works. Okay, so we have something, I used to call it just Sense It All, but nowadays, strictly speaking, it's actually Sense It All as a potentiostat. It accepts either our sensors or our screen printed electrodes. So ZP has a list of sensors and some of them are already active on this platform. But if the sensors don't exist, you have to use the platform as a potentiostat in order to develop the sensors. But ZP has the electronics, which we call Sense It All. We have either sensors or screen printed electrodes, which connect into the platform. And when I mean connect into, I'll just change my camera just really quick. I mean, this is a really elegant way. You know, this is let's say the sensor itself. It just keys in like that, and I click it closed. Instruments like this in the past have sometimes had slots. They've sometimes had cables. Real people, let's say, you know, in quality engineers or water engineers, etc. They're really not that interested in. Well, they're actually engineers, so they don't mind slots and cables so much. But sometimes you will find, you know, there are technicians out there that you really have to give them a very kind of simplified workflow, and this does actually have a workflow even in just connecting the sensor like that. Now onto it today, I'll put a 50 microliter sample. 50 microliters is a significant number because what I mean by that is that if you're in a water quality, water testing, you've probably got liters of material, you know, hundreds of liters. It doesn't matter so much. But when you're actually working in other applications where, you know, it could be blood testing, for example, the smaller the sample, then the more beneficial and more easy it is to use because then you're not having to draw blood, etc. So all electrochemistry generally requires is 50 microliters and actually less. We've got the app. The app is very flexible. The app is not menu driven. What I mean by that is you don't have these end users scrolling through endless apps. It's actually all QR driven. Um, Most people born post 2000s actually, um, the idea of Windows software with lots of options and, you have to really learn the software. That's gone away actually. That learning curve just got a lot shallower, I would suggest, because in fact this instrument is purely QR codes driven, and I'll give you a demonstration of that shortly. That QR code will be scanned by the app. The app will tell the meter what to do, and the meter will give the data back to the app. Now, what it's actually doing is an electrochemical measurement. As I say, those electrochemical measurements could be amperometry. So if you're trying to do glucose monitoring, lactate monitoring, oxygen monitoring, amperometry is a good technique for you. If you're trying to do pH or phosphate or potassium, then open circuit potentiometry is good for you. Impedance spectroscopy, good for immunoassays or proteins, etc. So there's all sorts of QR codes available, and those QR codes drive what the app is meant to do. The app drives the meter, and the meter gives the data back to the app. This is the significant part. It actually automatically uploads the data to a system called Julie. Julie is a cloud system from Zimmer and Peacock. And in Julie, we have a data pipe built in. So what that means then is that the raw signal comes in, we can pre-process it. So if there's noise on the signal, we can filter it out. You can essentially program this pipeline once, and then from there onwards, it will always do the same thing. So this is significant because once upon a time, the big problem that people have in development and commercialization is actually going from raw signal to information. A data pipe that exists in this Julie cloud is that glue that goes from raw signal in to information out. So we have pre-processing in there, we have processing in there. So for example, the demo I'll do today, we tell it, go and look at the peak height in this region, record the peak height, put it through a calibration equation, and at which point then it will actually give out information, and the information in this case is actually a concentration, and the concentration actually go back to the app. So if you look at academic papers, most of them finish at technology readiness level number 3, because actually what they finish with is raw signal and a calibration curve. Because of the data pipe here, if we've got the raw signal, great, that's what the instrument gathers. If somebody's done the calibration, and that might have been ZP or it might have been your engineers, then we have the equation, and then we can essentially look at the raw signal, tell the cloud where to find, let's say, the true signal among all of the signal, put that through an equation, and then turn that back into concentration in this case. And I'll show you that in my demonstration. As I say, this will probably go too quick for you to do this, but this app, if you've got other colleagues or other stakeholders that you think need to know about this, they can install this app already on their Android, or they can install it on their iPhone. As I say, this is being recorded. Just checking it was being recorded. Yeah. And you will be able to do this later on. When you do that, it's going to install an app on your phone called Sense It All. Now, Sense It All, you probably don't have an account at this point. So at this point, you click here and you set up an account. What that's doing is it's actually setting up an account on a system called Julie. So Julie is a data management system completely developed by Zimmer Peacock, hosted by Zimmer Peacock. It's all ZP's technology. It has its own URL, which is julie.zimmerpeacock.no. So when you install the app and you say I don't have an account, you can fill in the form and you'll end up creating an account. What you're actually doing is creating an account on a sister system also called Julie, because the app is really a portal to a cloud system called Julie. So I'm just describing the kind of architecture to you at the moment. When you've done that account, you will enter your login detail will be your email, and you will have created a password, and you'll log in. All right. So quick recap, first of all, I'm very interested in commercializing or raising ideas from just technology readiness level number 3 to much higher. The part of our technology stack is actually this app. This app will run the hardware, and it's a conduit to the cloud. When you log into that cloud, what's going to happen is it's going to look for a QR code. It's going to say, can I access your camera? And it's actually QR code driven. This is important because if we're shipping sensors around the world, we want people to have a very slick experience. So we often just give them well, in fact, I might have it here. Yeah, in fact, I've got it here. For example, this is my chili sensor. They get a bag of chili sensors with a QR code on it. So that means that they can, essentially install the app, scan that QR code, and the system becomes a chili sensing one. That QR code would be for nitrate, that QR code could be for potassium. So you have to scan that code. There's really two sets of QR codes that we have existing today. QR codes that would be used by academics to develop sensors that don't otherwise exist because they really need to be in the kind of potentiostat mode, or there's QR codes because we've actually developed the sensors already and we've put them onto the platform already. Now, I must say here that, the nitrate sensor, for example, if you're measuring nitrate in seawater, that's one thing. If you're measuring nitrate in non-saline solutions, that's another thing. So our calibrations may have to be tweaked depending on the actual application. It's a if I could give you an analogy, if you're measuring glucose in a bioreactor, signal versus concentration would have some kind of relationship. If you were measuring glucose in blood, you would still have a relationship, but the calibration would be different because the sensitivities and offsets could be different. So just be aware of that. I'm just going to do a quick demonstration at the moment. Yeah. So this is my phone. I'm just going to click a button on my app, which is here, and I'm going to scan my own screen. The reason I've just scanned my own screen is it's just gone into amperometry mode. So if you work with academics and they're trying to develop, and hopefully they're trying to develop sensors and things on our platform, they can use it as an R&D instrument to do amperometric assays, lactate, glucose, oxygen, small molecule assays like that. If they're interested in doing ions, I'm just going to scan this. Then I've just scanned it and now I'm in open circuit potentiometry. So as again, ions would be things like calcium, magnesium, pH, sodium, potassium. If you're working with proteins, I think EIS, you probably end up doing an immunotype assay. Then EIS is the right kind of methodology for you. We also have linear sweep voltammetry, which will be useful for small molecules. And in fact, I will just scan that now. And now I have linear sweep voltammetry. So I'm showing you that there's two sides to this particular coin, if I can put it that way. One side of it is it's a potentiostat that can be used by developers. Cyclovoltammetry is on there, and square wave voltammetry. Square wave voltammetry is a pretty sensitive analytical technique, but you have all of those methods. So that would be something that would be very familiar, should be pretty familiar to somebody who does electrochemical sensor development. But then because the data is automatically sent to the cloud, we have a data pipe in there. So we're actually able to then turn those methods actually into analyte specific. All we're really doing is actually putting them through filters, picking out peak heights or areas under curve, put them through a calibration equation, and actually then turning them into analytes. And we're really able to give a very nice user experience. So, chili, ginger, pH, nitrate, total antioxidative capacity, glucose, potassium, testosterone, which is something that we've just launched as well. Now at ZP, we do have a lot of sensors. I will go quick. Glucose, oxygen, lactate, hydrogen peroxide, pH, chloride, potassium, calcium, alcohol, nitrate, nitric oxide, ammonium, uric, sodium, phosphate, ketones, sulfite, purines, fructose, NADH, skatol, androstenone, cortisol, galactose, glycerol, troponin, I, testosterone, carbon monoxide, malic acid, ferric reducing, I forget what FRAP is, but it's it's an ability to reduce in blood, total antioxidative status, ATP, adenosine triphosphate, good one for bacteria, oxidation reduction potential, urea, lactose, good one for milk, histamine, and creatinine, sorry. Right. Now, the ones that are actually already translated onto the onto this platform are pH, nitrate, glucose, potassium, and total antioxidant capacity. We're pretty capable of, in fact, purine has also been translated as well. So we're quite capable of translating sensors on there, but I just want to highlight the ones that have been translated onto the platform. Capability of doing is different from actually having done. So, I just want to make that sort of clear. The question could be, if ZP doesn't have the sensor, so for example, if ZP doesn't have a sensor, somebody might say to me, oh, all right, can you do omega-3? So, I mean, I happen to be a chemist and then an electrochemist by training. So I sort of, I tend to start with the structure and have a look at these acids. Omega-3 looks a little bit tough, actually, to be honest with you. But I did then do a quick Google. So, it's quite straightforward for me. I'll put the omega-3 in there and I'll put one of the techniques that I think may be useful, which is cyclovoltammetry, for example. So I'll do a quick Google search on that. And then the first thing I find on ResearchGate is omega-3 and fatty acid in milk. I can criticize this paper, but it does tell me fundamentally that somebody has actually done the work. The one thing about electrochemical sensing as a platform or a modality for doing analyte detection, there are, I don't want to say hundreds of thousands of papers, but I feel like I'm not being so hyperbole to say there's hundreds of thousands of papers out there. There's actually a gold mine out there. Anything you can think of, you'll find somebody has done something. So when I do that search, I find something. It doesn't make it ideal, but I do find something. So what I find is that they've done it in a beaker, and I find that they're using a reference electrode, a working electrode, and a counter electrode. So they're basically doing an electrochemical cell. If you really want to translate that out of that paper into a product, generally you have to go for something that's much more scalable in manufacturing. So I would argue screen printed electrodes. And obviously I'm very biased, and you would start using our potentiostat essentially. And then I've read the paper, and I've only had a little glance through it, and I can see what they're doing is omega-3 is not intrinsically very electrochemically active. It's got a lot of double bonds, which mean electrons that are but those double bonds are essentially I think they're essentially isolated from, they're essentially isolated from one another because there's a saturated carbon between them. It's not terribly electrochemically active, but what they've shown is that by actually raising the temperature a little bit, they can get an electrochemical activity out of this. When I was looking at this paper, I would actually suggest, and I haven't done the work for this, that actually what they would really need to do is do a catalytic material on the electrode that would help in the oxidation of this omega-3 fatty acid. I mean, in the end, temperature is just helping them to do something that's otherwise quite hard to do. Another way of doing that is actually to have catalytic material on there. I don't absolutely know, for example, but if I just threw out some comments like gold nanoparticles or platinum nanoparticles, that might be the kind of thing that you would try. But that requires some research, which ZP hasn't done. If somebody said to me, actually, I want to do protein detection, and when I think about protein detection, if ZP hasn't already done it, which we probably haven't because proteins are quite specific, I would guide them towards a particular paper that ZP did years ago when we were looking at HCG. I'm not going to heavily go through the paper at the moment, but it does say, you can use screen printed electrodes in order to really build an immuno sensor on top of that screen printed electrode. This is just a blocking layer to stop non-specific binding. The first slide here is just talking about how to fabricate the sensor. And then the second slide here is really when the protein binds. So when the protein binds, then we get a source of signal. In this case, it was square wave voltammetry. So the term protein is very generic. We'd have to know what the protein was. It really helps if actually the antibody already exists. And if the antibody exists, then it does make everything a little bit easier. I think in terms of sensing, things that are ZP that I think are fairly easy. Ions are quite easy. Quite is I've got to be very careful with that term. Small molecules are okay. Once you start getting towards proteins and you're starting to have to bring in things like antibodies, then it actually does have a longer development path. But when we originally did this paper, like every paper, it actually finished at technology readiness level number 3, because what we finished with was raw signal and calibration. These days, actually, I put this slide together this morning, and I realized that actually these days, because we now have a platform that can take raw signal, put it through a calibration equation, and give back information. We could have actually raised this to another technology readiness level, which we couldn't have done in those days. I was just talking to an academic yesterday, actually, and they said to me, this allows me now to actually test real samples much more readily. That means I can get into higher impact journals. I know this is the Sense It All webinar, but I thought that was kind of interesting, actually, that this would allow people to get, as they say, into higher impact journals, because now they can go beyond just the calibration curve and the raw signal. They can actually come back with information, which will be sort of potentially more favorably reviewed. I just want to talk about the current situation in academia, actually. The current situation, this is Richard Compton, University of Oxford. Richard and many other academics will kind of produce the same, not same, but they'll produce papers like this. There'll be a title to it. There'll be an introduction to it. They'll have some sort of mechanism. I realized that I was also asked recently about pigments as well. Pigments, molecules that are intrinsically colored are quite electrochemically active. So I just want a sidebar comment here. Pigments and dyes are slightly easier because actually they're quite water soluble. I just want to make a comment. Pigments and dyes are often electrochemically active. Just for your interest, electrochemistry in part comes out of the dye industry because those dyes were electrochemically active, and the first sort of molecules that people investigated by electroanalytical chemistry techniques was actually pigments and dyes. Now I'm going to go back to my main topic, which was papers today in the world of electroanalytical sensing will have a title, they'll have an introduction, there may be some sort of mechanism in there, there'll be an experimental section, and there'll be some raw signal. And in Richard's case, he's got raw signal versus concentration, and therefore he's got a calibration curve. And he also went on to do one extra, which was actually test real samples. He tested something called the bomb, for example, which is a very hot chili sauce. And then he has a conclusion. That is technology readiness level number 3. I think the inability then to take that on and actually start, commercializing it is what's really holding back academia. And with a super biased opinion, because we're the manufacturers, this can actually do, well, this does do that experiment, and it goes on to actually give a user experience that non-electrochemists, let's say real people, actually can actually use that instrument, for example, to measure analytes in the food industry. So now I'm going to talk about the sort of 2-year manifesto at Zimmer and Peacock. So at ZP, we think that it takes too long actually to develop technologies and get them onto the market. We generally say if it's in the point of need testing, we can get people to market much quicker. I do want to talk about the sort of the valley of death. So somebody has an idea, they're going to the lab and they do some work on that idea, and essentially the sort of funding starts to diminish the closer, the higher that technology readiness level becomes, because governments only really want to fund R&D, but they are actually also interested in the commercialization of a lot of this technology. But that commercialization is hampered. The hampering of the commercialization of technology is based on a human factor. Do people really have the experience to do it? An economic factor. Is there really a business model behind it? And thirdly, but only partly, because I don't want to overplay it, is also a technology hampering as well. So I think in the world of sensing, actually, we can close that valley of death gap. And it's not by, which governments have already tried to do, is pour in funding. That's been going on for 2 decades, at least in my industrial career, probably, and it probably started before that. But in fact, we can at least close the gap, through my super biased opinion, by using a platform that's both an R&D platform and a platform that's robust enough to actually be put into, let's say, the hands of real people. So we can close that valley of death by getting rid of instruments that are otherwise just lab R&D instruments, and actually replace them with instruments. I mean, when I say, this is not in the hypothetical. This instrument is much more akin to a consumer grade instrument. So if you want people to really use technology outside of the lab, it has to have a much more consumer experience. And we live in a really cool time, actually, where you can develop technologies like that are much more sort of user friendly. Just to talk about, we think that we can get most ideas to market much quicker than historically would have been the case. We're basically trying to accelerate that, and we're trying to say that rather than take 5 to 15 years, which most ideas, most people working on commercialization for 5 to 15 years, and at the end of which actually they're not successful. The attrition rate is really high. We say, oh no, you can do this a lot quicker, but you have to take pointers from the technology world. I mean, in the technology world, if you have an app idea, um, you actually end up, for example, running part of your services on Amazon servers. You don't go and buy a server, host that server, maintain that server, and then run your technology on top of that server. But really, in the deep tech world of sensing, people build everything from scratch. They think that they actually have to build everything from scratch. I think we're actually better off taking more of um, a lead from the technology industry, which is what's existing, what can I integrate in order to achieve what I want to actually do? And so I'm sort of going to suggest that this Sense It All platform is actually a technology that, for those who have got a mind to get to market and be more integrators of existing technology rather than thinking that they have to invent and design everything from scratch. So if I've got a 2-year manifesto, then we have to take away some of these impediments. So the fact that this hardware and this app already exists takes away things like technology concept. It takes away system prototyping. It takes away system complete and qualified. It takes away system deployed. System deployed, you can actually download this app already. I was seeing somebody comment on LinkedIn the other day that, they would much rather see a prototype than see, I think it was a sort of, either a business plan or something like that. Well, of course, this can actually be very rapidly become a prototype. It is a prototype. So when I'm saying that we can shorten time to market, it's because actually we're taking away some of the technology readiness levels that would otherwise be something that a company would have to singularly work against. So at ZP, we actually think that the effort that people, if the sensor doesn't exist from ZP, we've got a very good platform in place, but there are parts that may still have to generate, which is the assay itself. If it's a protein that ZP hasn't worked upon, somebody has to work upon that protein. They have to work on so that's the biochemistry side of it. They have to work on the method file for it. So for example, square wave voltammetry or EIS for a protein. They have to do testing in the lab. They have to come up with raw signal versus concentration and a calibration equation. If people can do those 3 things, then they're basically ready to come onto our platform. That's only if the sensor doesn't exist. I think the path today is that actually people are basically doing all of the elements that otherwise exist themselves, including maybe printing their own electrodes. And it just takes too long. And the failure rate is 90%. And actually it takes 5 to 15 years. I kind of realize that your career span, if your career span is 30 to 45 years, you only get 3 bites at it. So if you spend 15 years taking time to fail. So I think people should actually just say, if I can't do this in 2 years, I should really sort of rethink what I'm doing here. Just want to say though, that at ZP, we're quite open to other people screen printing, making the sensors. We actually have design rules online so people can actually build to our platform. So our platform, if I could describe it, is really, it's an instrument, it's an app, and it's a cloud system to process that data. If there's a really strong wish that people actually want to manufacture, sensors locally, we do have our design rules out there so they can do that. Of course, you just then have to be responsible for the reproducibility of those either screen printed electrodes or the reproducibility of those final sensors. As I say, you can start trying this technology out for yourselves by scanning this particular QR code. Just the final QR code. I'm going to actually scan this QR code myself. This QR code is the end point. This QR code is designed to actually say you can reskin this app and it can become your product. So I'm really, the whole structure of this Zimmer Peacock technology is actually that this is one day in the hands of an end user that's really your client. And actually, we're not even represented in any kind of logo or badging on this. You can see it's actually quite plain. There's only one little logo just around here, and that's easy enough to kind of, we're not that interested in actually being the brand owner and that customer owner. It's not in our mindsets to actually do that. And so we do have actually built in a QR code system to even get us out of the app, let's say. So everything is then replaceable. So eventually this can become somebody else's. I just want to make this one of the final comments that this workflow is super simple. And I did not train either of these engineers to be able to run this particular instrument. They just sit behind me and they just good listeners, that's good, but they can actually run this instrument. So I'm really sorry, but what holds most technology at technology readiness level number 3 and stops it getting to market is actually the sort of complexity of the instrument. But if I can get a fairly bright 10-year-old to run this, then I'm really sorry, but this is actually a very scalable technology. And so I have at least proven to myself, and the fact that ZP ships this around the globe to many people, and people are having a good user experience on this. So I'm going to wrap it up, I think. Let me just go to a quick slide. Yeah, I'm going to do a quick sensor to cloud demonstration. I know some of you have seen something similar in the past, but I'm going to talk more about the actual cloud side of things now. But the first thing I need to do is share a different camera with you. Right, that's kicked in. I'll stop sharing that so it becomes a little bit bigger. In fact, I'm going to move to, I want to move to the right. Yeah. Just going to connect to this. I'm just connecting now, which I've done. So I can see the device. I've connected to it, so the device is connected. I'll go into here. This is just so I can remind myself where I can find my data later on. I realize that's a little bit bright, but I've got a bad cable I have. Right. Right, so what I'll do is I'll put the sample on. I've got a bit of a bad cable. That's my fault. Okay, so I'll put the sample on and I'll run it real quick. So I will connect. I will put the sample on. Just going to give myself a second cable because I realized I did need to actually throw that cable out and put this cable in. Better. Right. Okay, so connect to the device. Done. I will go to assay, start, and off it goes. Right. So I'm doing that because I actually want to show you that there's a cloud side to this. So that assay runs pretty quick. But we also have a cloud side to this. I'm just going to navigate to my cloud. So this is my cloud system. If I just share my screen here, sign in. So we have a cloud system called Julie, and it sends. In fact, the app has just finished now, so I'll just share that screen just real quick, rather that camera. So the app has just finished because one thing we're quite good at ZP is actually making fast assays. Slightly different matter, but people, if they don't have a commercial perspective, they sometimes make assays that are just fundamentally too long. But at ZP, we do try to make our assays quite fast. With that said, I'm going to go back now to my cloud system called Julie. I'm just going to look in for a folder called demo. If I go into demo, I found my instrument. And then if I do my refresh, I will actually find my my actual data up here, for example. So I actually get the raw signal up in the cloud. Now, I also get a, make sure I'm sharing the right screen. I also get a number, concentration. But what it's done is, I'm just going to talk about the data pipeline a little bit. The data pipeline is this, that the signal has gone to the cloud. I've told it to look at part of what I call the second scan, because I did something called cyclophotometry. I've told it to filter the data. I've told it to flip the y-axis. So this is kind of pre-processing. So filter, flip the data around the y-axis, and then analyze. So pre-processing and then analysis. Show extracted value. Look for a peak height in this window. Look at what's called the reverse scan and fit it to this formula. So understand that most papers, in fact, when people publish a paper, they're manually doing this. Somebody said to me the other day, "Wow, that's great actually, because now I can just automatically process my data." But they're manually doing it. They're probably not filtering, but they are probably doing a peak height fit, and they probably are fitting it into an equation and turning it into concentration. So in fact, you can almost see that workflow here. There's the first part of my signal. There's the second part of my signal. This, we flip the signal around the y-axis. Here, we've told it to open up a potential window, and we've told it, look for the peak height and turn it into concentration. And that's exactly what it's gone and done. And that's the bit that's, in the end, the user experiences, they just get the concentration. But you can always check the quality of the data as well, especially when you're in a kind of development phase where actually you're not entirely sure that end users are necessarily using it the way you want. So if I was to describe, this has been a live demonstration, as you can see from the fact that I was actually having to change the cable, but that will teach me. But you can see that I think you get a good sense of actually the robustness of this platform. So in summary, we have a technology stack that already has a lot of sensors on it, including glucose, chili, ginger, potassium, pH, nitrate. We have a reservoir of other sensors that have not yet been moved onto the platform, but are capable of moving onto the platform. The platform can deal with small molecules that we haven't tested today. I think the strategy is the best fitting scientific paper has to be found, essentially copied and translated onto the platform. If it's for proteins, then you have to know what the protein is. You have to identify the correct antibody, and an immunoassay has to be built. I did a quick demonstration, but this time around, I want to emphasize more of the cloud system, the way you actually got a data pipeline up there, which will take raw signal in. You'll filter the data. You'll tell it how to essentially pre-process the data, then how to do the analysis. You get a number, and that number comes back to the phone. So I appreciate you coming this morning. I wanted to do this in 45 minutes. We've done it in 43. So don't worry about notes, etc. I've recorded this, and I'll send you a recording shortly. Okay, take care and speak to some of you soon. I'll see some of you in Swansea very soon. Take care. Bye-bye.